My name is Emil. We are going to discuss general theory of relativity. So the goal of this lecture is to understand what means metric in space-time, what means general covariance, what are different coordinate systems, and what does it mean to make a transformation from one reference system to another reference system, and what does it have to do with change of coordinates. So for that reason, let me start to the easy discussion of the Minkowski space-time and of special theory of relativity. In special theory of relativity, we are dealing with flat Minkowski space-time, whose metric is famously known to be like this, where mu and nu are indices which are ranging from 0 to 3, and metric tensor has the following matrix, which is diagonal, and its diagonal components are as follows. As a result, we have dt squared minus dx vector squared, where x vector is just x1, x2, x3. And throughout my lectures, I will assume that the speed of light is set to be 1. So, what does it mean that we have a metric in Minkowski space-time, or in space-time in general? Well, let me start with the idea of Newtonian mechanics and metric in space. Suppose we have two-dimensional space, for simplicity, to draw it on the blackboard. And we discuss, for example, behavior of two cockroaches. One of the cockroaches stays still at some point, and the other cockroach starts its motion from the same point and moves somewhere. So in Newtonian mechanics, we usually discuss trajectory. We want to understand its length, how long was the path of the cockroach, etc., etc. So in Newtonian mechanics, we have a metric in space, and then separately we have a very naive metric in time, which has nothing to do with the combined metric on space-time. So what does it mean? It means that two cockroaches, both the one who was standing and the one who was moving, spent the same amount of time during their motion. For example, the cockroach which was standing, its world line, its behavior in space-time was a vertical line, and the world line of the second cockroach was like this. And one would say that the cockroach during this sort of behavior became older by the same amount. It means that they started their motion at moment of time t0 and ended their motion at the moment of time t1. And both became older in Newtonian mechanics by t2 minus t1. The presence of the metric in Minkowski space-time tells us that the situation in special theory of relativity is completely different, because now time and space combine together in one continuum where we have a metric, which means that there is a way to measure distances in space-time between any 2 points in this space-time. It means that we can measure the length of this world line and separately the length of this world line. Obviously, as we know from special theory of relativity, the length of this world line divided by the speed of light is just the time spent by the cockroach moving along the corresponding world line. Say the first cockroach, which was moving along this world line, which was standing, this cockroach has spent exactly this time, this proper time, while the cockroach which was moving now spent a different proper time, which is not equal to t2 minus t1. It's the length of this world line, which is equal to integral over ds over this world line. And this is not equal to T2 minus T1. In fact, one of the cockroaches is older than the other. Now, this cockroach, in fact, is older than this one, because this line in Minkowski spacetime is longer than this line due to this minus sign in the metric. So, Minkowski metric is given by a very special bilinear form. Very special bilinear form. Metric is in one-to-one correspondence with the coordinate net. What does it mean that we have a coordinate net? One can draw in space-time T x1, x2, t. By the way, these pictures are, of course, not quite adequate because I am drawing on a two-dimensional Euclidean plane of the blackboard. I'm trying to draw three-dimensional part of Minkowskian space-time. This picture, of course, is not sensitive to this minus sign, and that one has to bear in mind while describing or considering these pictures. So, how do I do a coordinate net? I, for example, fix planes x1 constant in equal dispositions along x1 line. So it means that I have this plane, I have this plane. The same I can do along x2 constant and along t constant. This way I will get some hypercubical coordinate lattice which is corresponding to this bilinear form specifying Minkowskian metric. This bilinear form is invariant under the following coordinate transformation, which is known as Lorentz boost. It is given as follows. We have transformation from t and x1 to t bar, which is t hyperbolic cosine of alpha plus x1 hyperbolic sine of alpha, x1 bar t sine of alpha, hyperbolic sine of alpha, plus x1 hyperbolic cosine of alpha. At the same time, we do not change x2 and x3. And alpha is constant, which means that it doesn't depend on the coordinates. The physical meaning of this transformation is that it takes us from one inertial reference system to another inertial reference system, and the second inertial system moves with velocity v with respect to the initial one. Then cosine of alpha is nothing but the relativistic gamma factor, which is as follows, and sine of alpha is just minus v divided by square root of v minus v squared. And v is constant. So we have two inertial reference systems. So this coordinate transformation doesn't change this bilinear form and takes us from one hypercubic lattice, coordinate lattice, to another hypercubic coordinate lattice. But let us consider an arbitrary coordinate transformation. For example, let us consider the transformation from x mu to x bar mu, which is an arbitrary function of the initial coordinates, not necessarily linear. Under such a transformation, the bilinear form will change unrecognizably. But at the same time, the distance between any 2 points in space-time will not change. Notice that I do not deform the initial space-time. I do not shrink it, I do not expand it, I do not bend it by any means. I just choose different coordinates in the same space-time, different coordinate lattice, meaning that I draw these hypersurfaces of constant x mu along each direction. Coordinate lattice will look horribly. It will not be hypercubical. And also, this bilinear form will change unrecognizably. For example, the metric, as we will discuss in the next lecture, metric changes as follows. We take from G eta mu nu, from eta mu nu to a metric tensor, G mu nu, which is as follows. dx alpha dx beta divided by dx mu bar dx nu bar. And because of this transformation, we will discuss it in greater details in next lecture. Because of this transformation, we observe that the line element ds squared doesn't change. Originally, line element was eta mu nu dx mu dx nu, and now it is just given by g alpha beta of some function of x bar now, not necessary constant, dx alpha bar, dx beta bar. Because of this transformation, we have this equality, that this is equal to this, and line element interval doesn't change. So now arises a natural question. If we have such an arbitrary, not necessarily a linear transformation of coordinates, what does it mean physically? If we start from inertial reference system, where do we go? What reference system do we obtain? Do we obtain a reference system? Now we are going to address this issue.